Okay, I think we can start. Welcome everybody, thanks for coming to my talk. And first, a little bit about me. I've been a regular here, but for people who don't know me, I am a software engineer at Bloomberg LP, and I work in the London office. And I've done a few video courses on modern C++ that are available online. And I started my C++ addiction with some hobby game development projects, but that was a long time ago, but I still have some tutorials and games available online. And I participate in standardization. I have 2 papers, one of which we're going to talk about today, and also like to write articles about crazy metaprogramming on my blog. And finally, I like giving presentations. I've been around quite a lot, and I really enjoy sharing my knowledge and meeting people at conferences. I have a bunch of open source projects, and also I'm one of those weird guys that's there on Stack Overflow to answer your questions. Okay, so what are we going to talk about today? So we're going to start with an introduction about higher order functions, what they are, and how we can use them in our code, and how we can implement them. And the second half of the talk will be about function ref, which is a proposal that is in flight for C++ 20. And I'm going to tell you about why this exists, how it is specified, how we can use it. We're going to see an implementation, and then I'm also going to cover a little bit of open questions, a little bit of problems, and I would like your input on that. And finally, we're going to see some benchmark of this thing against std functions and other things. This is not going to be a talk on functional programming in general. I know we all love functional programming, this is C++ now, but I wanted to make this talk a little bit more accessible, especially for people who cannot go fully functional in code bases that exist in their companies, but want to slowly integrate things that are not so controversial, but still very helpful for the quality of the code. So what we're going to look at mainly is practical everyday uses of higher order functions and how we can use existing functional facilities in the language, and also an example of design and implementation of ISO C++ 20 proposal. Assumptions, this is C++ now. I given these talks at other places, but I hope and assume that all of you are somewhat familiar with Lambda expression, templates, and modern C++ features. But please do not hesitate to ask any question if you have any doubt or if you want any clarification, or just heckle me or contest what I'm saying. So, higher order functions. How many of you know what a higher order function is? Okay, quite a few people. So, in general, what Wikipedia says is usually a good start, and in this case, I tend to agree. Higher order function is just a function that either takes another one as an argument or returns another function as its result. So in C++, we can see a very simple example over here. We have a function called callTwice, and we accept some sort of callable object f by forwarding reference, and then we invoke it twice in the body of the function. And then we can call this callTwice abstraction, for example, with a lambda over here that prints out hello, and the result of this code will be hello, hello printed out to stdout. So in this example, we take in a function object as an argument. We could extend this through a callable if we use the std invoke. And for this particular use case, I'm using a template parameter, but I could also use something like std function or function pointers, depending on what I want to do. So this is an example of the first kind. The second kind, which returns another function, we can see here with greater than. So in this case, we have this function called greater than. It takes a threshold, and then it builds a closure through a lambda expression where we capture the threshold by value. We accept some value x, and we return whether or not x is greater than the threshold. And then we use our auto return type to basically return the closure without any extra cost. One way we could use this is in conjunction with an std algorithm. So we could say std count if over a bunch of numbers, and then we create our predicate on the spot by saying greater than 5, and this will return the closure that is the predicate to the algorithm. And in this case, our result will be 2. So again, this is a second kind of higher order function. It returns an invocable that is our predicate, and we're using lambdas and auto return type to implement this, but we do have other choices. So another question. Do we have any higher order function in the C++ standard library? Yes. Examples? Algorithms. Yeah, algorithm is the most common one. So that's easy, a little bit harder, maybe. What about the C standard? Qsort, okay. Anything? Bsearch, anything weirder? Yeah, I like that. So even in the C standard, we have a bunch of things. Obviously, the first ones that come to mind are Qsort and Bsearch, which are algorithms. But even things like addExit, addQuickExit, which allow you to set some callback that's going to be executed when you exit the program, technically are higher order functions. And there's also another one, which is signal, which I chose as an example, which is not very commonly seen, which technically is also a higher order function. And what signal does, it basically takes some int signal that you want to handle, and then some signal handler over here. And it says that this can be set so when a signal is raised, the user-defined function is called. Now, if we look at what the signal handler is, since this is C, it has to be weird. So we have two macros over here that are basically predefined handlers. And then you can also pass a pointer to a function that takes an int and returns nothing. And an example of using std signal would be this one over here. We just invoke it with, for example, sigint. And then we say whenever sigint is raised, we're going to invoke this lambda over here that accepts the number of the signal and then prints out something to stdcout. Now, technically, this is completely undefined behavior because there's just a few things you can do in a signal handler, and printing is not one of them. But I don't really care. And for the sake of this example, it just works. And one point I'm trying to make is that high-order functions come in all shapes and forms, not just algorithms. Lambda expressions, as you've seen so far, work really great with high-order functions. And also, in this particular case, stateless closures, so lambdas that do not capture anything, are implicitly convertible to function pointers, so they do work with something like std signal. In the C++ standard, we mentioned algorithm and numeric, which are the most common ones, but we also have a bunch of other things. On the same vein as at exit, we have setTerminate, and also we have utilities to, for example, work with tuples and variants like visit and apply. Std invoke technically is also high-order functions, and then also bind and bind front, which are the second kind, are functions that return other functions that you can call with bound arguments. There's plenty more, so this is just a few examples. One of the common uses of high-order functions that I especially have seen in game development is the erase remove idiom. So how many of you are familiar with this? Great, pretty much everyone. So this is a very common pattern, and what it allows you to do is basically remove all the elements from a contiguous container that match a certain predicate. And this is useful because the way this is done under the hood is by moving all the elements that match the predicate to the end of the container, and then doing an eraser in a single pass without... I know what you're going to say. Sorry, it moves all the elements that do not match the predicate to the beginning of the container, and then it does a single erase from that spot to the end of the container, so you can remove them very efficiently without having to shift everything over and over. And I'm being careful, Peter. And another important thing is that also it preserves the relative order of the elements, so that can be useful in some cases. And in general, this is a very good way of doing it efficiently without having to reinvent the wheel. And as you can see here, the way it works, you just call removeIf with the range and the predicate, and this will return an iterator to the beginning of the range of the elements to remove. So then you can call the erase on the range returned by removeIf and the original container, and you will remove everything that matches the predicate. Another example is with std variant. So if you haven't seen variant before, it's just a discriminated union of different types. In this case, maybe we're modeling some sort of networking application where we can have events coming from the wire, and they can be a connect, disconnect, or heartbeat event. And then maybe we want to process a generic event and do something different depending on what underlying type is active in the variant. So instead of doing an else-if chain, which is very imperative and hard and easy to get wrong, for example, you can forget to handle a particular case, or you can have issues with adding new cases in the future, what we can do is use this little trick. We overload a bunch of lambdas together to create some callable object that accepts all of the alternatives of the variant, and then each one will have its own different behavior. And then we pass this overload to stdVisit with our variant. And what happens is, for example, if we process an event with a heartbeat, this is going to find this overload over here and print out process heartbeat to the console. So this is kind of very primitive form of pattern matching. Obviously, we have proposals in flight to make it better and part of the language. But this works. And if you're interested in seeing this and also extensions such as recursive visitation and how it's implemented, you can see my talks ACCU and C++ 2017. Yeah, Attila?
Silly question. Can this overload be implemented in C++ 11, or do we need a later standard for that?
You can implement in C++ 11. You can do it recursively in 11. So the question is, can you implement the overload function in C++ 11? Yes, you can. it will not be pretty because you have to do it recursively, while in 17, for example, it's just 3 lines, and you can use a pack expansion on a using statement to expand all the overloads in one place. So in general, what use cases do we have for high-order functions in, I would say, day-to-day programming in a big corporation? I found that the most common ones are avoiding repetition, inversion of control flow, asynchronicity, and compile time metaprogramming. There might be more, and obviously if you're doing something a little bit more functional, like a lot of composition and creating a framework based on that, is going to be based on composition of higher-order functions, but this is more like practical everyday uses if you're not going fully functional. Avoiding repetition, I think we can all agree that repetition is usually a bad thing. It leads to bugs and maintenance overhead. Obviously, there's a trade-off there. Sometimes avoiding repetition might be not worth it, but that's just, it comes with engineering experience when it's worth removing it. And in general, sometimes it's very trivial to avoid, so you don't need any high-order function. As an example, over here, we had this integration test for our routing application, and we were basically spawning a bunch of machines with a unique port on localhost, and we had this context thing that basically provided us with unique ports, so machine 0, 1, and 2. And there's a little bit of repetition here because we are passing the same IP address over and over to the reserved port call. And you can imagine if, for example, you want to change this IP in the future, or if you want to change the way you reserve the port, then you would have to change it 3 times throughout the whole integration test. So now with Lambdas, we have a very quick and cost-effective way of introducing a local function. We don't really have to document it or give it a very detailed contract. So what we can do is simply have this Lambda over here called getPort. We abstract the idea of reserving the port inside the body of the Lambda, and then we can simply use getPort over and over again to achieve the same result as before. And I would say this is a good trade-off because if in the future we want to change the way this is done or the IP, we just change it in one place. So this is a simple example of when you don't need extra power to do this kind of refactoring. Other times it can be more complicated. So this looks like an artificial example, but it isn't. I was actually working on a GUI system for a game a bunch of years ago, and I didn't implement it in a very smart way. So I basically had to do 3 passes over my widget hierarchy. The first one was to basically recalculate the focus of all visible children, then recalculate the boundaries because the focus might affect the boundaries of where you can click with the mouse. And then finally, after I do those 2 steps, which depend on each other, I could call update on the children and go recursively down the hierarchy. So this was the best way of doing it, but I still had this kind of repetition in my update function. And again, I think it's worthwhile abstracting this away in order to avoid making mistakes in case I want to remove a pass or add an extra pass and have a little bit of leeway in the way I change the code in the future. So one way you can abstract this is by, again, introducing a local function. In this case, it's going to be a higher order one because it accepts some action f. And what you can do is give a really nice name to this function so it becomes really obvious what it's doing. So in this case, I decided to call it for visible children. And then you pass an action f, and you abstract the control flow away inside this local function, which is going to loop over the children, check if a child is visible, and if it is, it's going to invoke the action on the child. So now I can express my business logic, the logic of going step by step in a very straightforward way, and I can just say, for the visible children, recalculate the focus, then the bounds, and then update. So I basically have my control flow in one place, I don't have to repeat the control flow, and the business logic becomes more clear and easier to understand. Okay, so what about other use cases? I mentioned inversion of control flow, and this is basically when you want to pass an action and predicate to a function and let it deal with the control flow. So separation of what is happening from how it's happening. And I think that the prime example of this is C++ 17 parallel algorithms, because they exactly do this in a very, I would say, extreme way. So imagine again with this other example, you might have some sort of simulation of physics, maybe particles, and a physics component might have some mathematical vectors of position, velocity, and acceleration, and you just want to integrate this each frame of your simulation. Then you might have some sort of vector containing all your particles in the contiguous storage. And then you can use a C++ 17 parallel algorithm over here that basically says, okay, go through all the components with this execution policy called parent-seek, which basically allows the compiler to execute this in multiple threads and also with vectorization and whatever you want. So it's going to give a lot of freedom to the compiler to optimize this. And then what you do, you pass the action that you want to be executed as part of the for each call. And in my opinion, this is a very, very clear separation of what you want to happen compared to how it's happening. So you're giving all the freedom to the compiler to do whatever he wants to execute this operation, and then you're giving the operation in a separate step. So why is this a good thing? So not only gives you performance benefits, but also both the control flow and the action can be tested and reused separately. So you can imagine that a complicated algorithm might be easier to test if you have a simpler action, or a complicated action might be easier to test outside of the algorithm where it's going to be used. So this kind of thing is useful to enhance your code quality and reusability. Another example is printing a comma-separated list of elements. So this is something that comes up quite often, and people often use for loops with state or stuff like that, and it's quite annoying to see that in the middle of business code. So what you can do as an initial version is obviously create some sort of concrete algorithm, which is not really generic. So in this case, it is parameterized simply on an std vector. And then you can say, okay, if the vector is empty, I'm not going to do anything, I'm just going to return. Otherwise, I'm going to print out the first element, and then starting from the second element up until the end, I'm going to print out a comma with a space, and then the value. So this is a reasonable first version to print out comma-separated list of elements. Now, what I like to do when I see this kind of algorithms is, okay, let's make it generic. So I like to identify the structure, and I can see that I have basically the empty check, then my action, then the loop from the second element to the end, then my separation action, and then my action again. So I have these two elements, which are good customization points for the user, so that they can choose whatever action or separation they want to have in their code. So once I do that, I can create an abstraction by simply replacing those comments with calls to user-provided actions. So in this case, I call this algorithm for separated. It's not the best name, but at least it gives you the idea of iteration and adding separators between elements. It takes a range, an action, and a separation action. And then it's basically the same thing. I check if the range is empty. Then instead of printing, I just call my f action on the first element. Then I go from the second to the end. Instead of printing a comma, I just call my separation, and then I call my action again. So you can use this, obviously, to re-implement the original function, which was print. And the way you do that is by simply calling for separated on the range. Your action is going to be just print out something to stdc out, and your separation is going to be just print out the comma with a space. That's going to be exactly the same as before, but the benefit is now that for separated is reusable. It provides the control flow, and the user provides the action. So you can test everything separately, and you can reuse for separated for other things. As an example, you can, for example, if you're writing some sort of command line application and you want to make some test more emphasized or explicit, what you can do is define this wide print function that, given a string, it prints out to the console with a space in between. So one way you can do that, you simply call for separated with your print action, and instead of putting a comma, you just put a space between all the elements. Yep.
Not really a question, more like a point that
Yeah.
we're getting OStream joiner in C++.
Yeah.
That's basically the same thing.
So the comment is that we're getting OStream joiner. I was at Jeff Talk yesterday, so yes, forgot to mention that, but there's going to be a utility in C++20 that basically does this for you, and I think it solves the problem of people going on Stack Overflow every day asking how do I print stuff with a comma in between, which is really good. Yeah.
Can you pass lambdas as default parameters in these functions? I never tried it. Yes.
Okay. So the question is, can you pass lambdas as default argument? And Ben says yes if they don't capture anything. I think that's right. I'm not sure if it's even more, there's more leeway in C++20 because of lambdas in unevaluated context or stuff like that. But you should be able to do that. I'm not totally confident. We can try that later. You know, the worst case scenario, just you make a struct and you get an instance of the struct.
Tori, what did you call that particular application?
Which one?
The one where you're passing in the different functions as arguments and causing a framework?
Inversion of control flow, is that what?
You just had it. You're passing in different behaviors, and you're constructing a framework. No?
This thing?
Yeah, maybe I misread it. Never mind.
Okay,
okay.
we can go back later. Okay, a more realistic example, we actually had this in production. I was basically working on a broker application for trading systems, and the idea was that we get a bunch of data from trading system of different formats. It goes into the broker, we normalize it, and then we pass it on to consumers. And one way we designed this is that basically we had an order set of active systems. So they were things that were actively producing data. And before marking them as ready to synchronize, we want to make sure they are initialized. So we did some steps at the beginning. We marked them initialized, and we moved them from a set to another to basically keep track of the ones that are ready to produce data. And what we did was basically invented this very small algorithm, which is called consume if. And what it does, it takes a range, a predicate, and an action, and it goes through the range. In this case, it's going to be another set or another map, so it's not a contiguous range. And it checks if the current element satisfies the predicate. If it does, it will invoke the action on it, and then it will remove it from the current set and update the iterator. Otherwise, it will be skipped, and we simply move forward. So the important thing about this algorithm is that often people forget to do this operation over here. When you erase from a map or another set, you need to set the iterator again if you're in the middle of a for loop. Otherwise, they will be invalidated. And also, it allows us to basically change our container in the future without altering the user code if we want to change the way we consume elements, for example, from other type of containers. And the usage is quite straightforward. We pass our systems, which is the unordered set. We check if they are initialized, and if they are, we change the state ready to sync, which means we remove them from the original set, we put in another one, and change some state inside. Does that make sense? Okay. Another use case is asynchronicity, and I think that currently high-order functions are the easiest way of expressing asynchronous callbacks. Think of std future, std thread. But in general, many use cases might be superseded by coroutines. Unfortunately, we do not yet have a proper implementation of those, but in the future, these might be different, so you might want to prefer other techniques to do that. An example of asynchronicity that's a little bit away from the standard library is something I presented in 2018. This is basically a way of creating futures without any allocation or type erasure. And the way it works is that basically you can create a graph at compile time with some operations and combine different operations like wait for all of these things to be done, then execute this, then wait for any of these things to be done, and so on. So this graph in particular starts with an all node. It takes two lambdas. The first one will they both do a get request for some image on the internet. And once both of them are done, this is executed in parallel, then it triggers this lambda over here, which accepts a payload with the two data items from the previous node. And then you can apply some functions of this like stitch to create your collage of images, and you can send it forward to some other place. So the idea here is that by using high order function, you can compose these things at compile time, and then the execution is going to be done by the runtime engine, which will be able to put it in parallel where possible. And lastly, metaprogramming. I think that high order functions are probably one of the only ways we can currently express algorithms at compile time. So if you think about Boost HANA or things like that, they all behave in this model where you pass high order functions, because we don't have anything like constexpr4 or anything like that. So I wrote some articles on this. The links are in the slides if you're interested. But in general, what you can achieve, for example, is create some abstraction like this one, enumerate types, where you pass in a list of types like int, float, and char, and then you provide some sort of lambda. In this case, it's a +20 lambda that uses the template syntax. I think Louis was the one that proposed this. And what it does, basically, for each type you pass in the parameter list, is going to invoke this lambda, passing the type here and its index over here. So the first invocation is going to be int 0, then float 1, then char 2. So it's kind of like Python enumerate at compile time over a list of types. And in this case, if we simply print out the index and the type ID name of the t, what we get back is 0i, 1f, and 2c. So it's quite easy to express these algorithms with high order functions. And there are some proposals in flight like expansion statements that could do this generation for you, but currently there's nothing like that in the language. Okay, another interesting thing that I researched as part of this talk is how higher order functions compare to other abstractions when both can achieve the same result. And I compared higher order functions against RAI guards and iterators, but there are probably other things you can compare them against. It's interesting about this one. We had this problem in Bloomberg as well. What we basically wanted is a way of ensuring thread-safe access to a particular object without relying on the user manually locking or unlocking something or using a lock guard. So imagine we have this foo class over here, and we want to instantiate the synchronized foo wrapper, and the synchronized foo wrapper forces the user to access the underlying foo instance only after a lock has been taken. So it prevents the user from making a mistake and just gives you thread safety for the foo instance. So now the problem is, what interface do we expose that allows the user to access the underlying foo? We have a few choices, two of which are RAI guards and higher order functions. So let's see how they compare. So the first one with guards works a little bit like this. You call sfoo.access, and it gives you back some guard. You can put it in an f variable. The type is unspecified. And then if you use star operator or arrow operator, you can actually access the underlying foo instance, and that's guaranteed to be thread safe. So if you imagine how this works, it basically, when you create the guard, it locks the mutex for you, and then it gives you access to the foo instance. And when the guard goes out of scope, it unlocks the mutex. So that's one way you can guarantee that the user never forgets to do it. Alternatively, what you can do is make access a higher order function, and what you pass in is the action you want to be executed on the underlying foo instance. So in this case, it's just a lambda. And then you're gonna implement your behavior inside of the body of the lambda. So from the perspective of the user, we have some pros and cons. For the first version, it is more friendly to control flow. You can imagine using this, for example, as part of a loop. You can use break, continue, and return without any problem. While in the second case, if you try to return from the lambda, you're just going to return from the lambda, but not from the outer function. And also, if you're trying to use break and continue, it won't work. Also, the second one might require captures for the underlying scope, and it's more unfriendly to composition and control flow. However, there's one big advantage for the second one, which is it's trivial to implement compared to the first one. So we lose in, let's say, flexibility for the user, but we gain in implementation easiness. Ben?
It also supports a more declarative style. You could return some internal sfoo by value, which on the left-hand side you have to declare the thing, then assign to it.
Okay. So the comment is that the second style is also more declarative. For example, you can return the foo by value, while in the second case you might have to declare it outside after getting the guard. Yeah, that's fair. Okay, so what I mean with implementation complexity. So the first one is obviously not that hard to implement, but what you have to do is create this access function. Inside of it is going to have some access guard object that contains, for example, a lock guard. And then you would have to implement the constructors, the star operator, the arrow operator, all the boilerplate that makes it work and provides the interface for the user. And then what you do, you simply return this access guard. And in this case, I'm deliberately using auto here. So this is kind of an implementation defined type. This works, but it's a little bit of code that needs to be tested and reviewed. On the other hand, if you want to use the second syntax, then it's super trivial. What you do is simply get your lock guard and call your action on the object, and that's it. So as you can see, depending on what kind of interface you want, the second implementation is way easier to understand and review. Yeah?
Why is the return type of access not decal type auto?
The question is, why is the return type of access not decal type auto? It should be decal type auto, yes. That's a bug. Ben?
In the first one, you probably want to put no discard on it. And I don't think there's a way to propagate the no discard of the internal function on the second one.
So the comment is, on the first one, you want to put no discard on it. I completely agree with that. I consider this a bug as well. And what was the second point? I'm not sure I catch that.
The second one, like, there's no way to propagate no discardness of the
Oh, for the second implementation. Yeah, okay. And there's no way of propagating or discard or the function for the second implementation. That's interesting. Maybe we need something like that. It's interesting. Okay. Also, another use case that's super similar is benchmarking a function, for example. So a quick and dirty way of benchmarking the execution time of a function is by using Chrono. You can use high resolution clock, get the time before you call the function, invoke your f, and then basically calculate the time elapsed by subtracting now with the time of the initial call. Obviously, this is not very statistically accurate, but it does the job if you're trying to prove a point in a code review. And again, you can do this either by providing some sort of guard that does the timing on construction and prints out the time on destruction, or some sort of function that accepts an action and then gets the time, invokes the action, and returns something. So there's multiple ways you can do that. Other abstraction, iterators, and in general also ranges. In this case, a range is just a pair of iterators, so I'm conflating them together. Imagine iterating over a filtered range. So you have your vector of ints, and then you want to filter all the even integers and do something with them. So one way you could do this is by providing some sort of filter abstraction, which works with a range-based for loop. So this implies that filter will have a begin and end and expose some sort of iterator type that does the filtering for you lazily. Now, this is very good because it's friendly to control flow. You can use break, continue. You can compose it with existing iterators, with STD libraries. However, the implementation, again, is complicated and way more complicated than the one on the right-hand side. On the right-hand side, if we use something like for filtered, where we pass the vector of ints, then our predicate, and then our lambda, then we have the same problem as before. Is unfriendly to control flow. It might require you to capture things. It doesn't compose well unless you have your own system of composition with IR functions. But if you only need filtering, then it's super simple to implement. And as proof, let me show you the synopsis of filter, iterator, and boost. I mean, it's obviously, if you know how iterators work and you know how ranges work, you can definitely implement this. But if you are doing it from scratch and you cannot use boost, it's hard to justify the amount of work you have to put into this, depending on how many times you use this abstraction throughout your code base. On the second case, even though you might be using this for filter 1 or 2 times, maybe in test drivers to make the logic a little bit nicer, then I think it's justifiable to simply provide a function like this one, which has internally a loop, checks the predicate, and calls the function for you. It's not as flexible, it's not as elegant as the other one, but it's simple to implement, simple to review, and it might be the best choice if you are not trying to provide an abstraction for your users, but just make some piece of code a little bit nicer. So be pragmatic about it, be reasonable. If you need to provide some sort of library utilities for your team, then take the time to do it properly. If you need something that's quick and dirty, but improves the readability of your code and prevents mistakes, then this can work really well. One more point that I want to make. I haven't explored this a lot, but if you think about it, in general, high order function iteration can also have performance benefits compared to ranges in some cases. So as an example, imagine iterating over interleaved or concatenated ranges, where the ranges have different types. So maybe you have some sort of sequence of names and separators, and you want to iterate first on a name, then separator, name, separator, and so on. So you create this sort of interleave abstraction, which takes a bunch of containers and gives you a way of iterating over them. In the case of begin and end, so ranges, then you need a single type. Obviously, you cannot have different types. So in order to make that homogeneous, you could use something like variant. So the iterator would return a variant over text and separator, then you do the dispatch or runtime to check what you're returning, and then you act upon it. However, if you use the high order function version, you can avoid the runtime dispatch and the overhead of the variant, because in this particular implementation, what you can do is simply generate a loop that first calls a function with the name, then the separator, the name, the separator, and so on. So you know at compile time how this thing is going to be called, and all you have to provide is some sort of overload over here that accepts a text or separator, and then you're not going to have any runtime dispatch or overhead of the variant. This is going to be resolved for you at compile time. So this is interesting. I haven't thought much about it. I'm sure that with ranges, there's no way you can do better because the type has to be homogeneous as they are iterators. But in the case of higher order function, you can do better, but still you would need a way of composing them in order to get huge benefits out of it. Does that make sense? So small recap. Higher order functions are quite powerful. You have many different use cases. And in general, if you're trying to solve a problem and it can be solved with a higher order function or a different alternative, they're easier to write, easier to review, but they are not as composable, not as flexible. So I would say be pragmatic, use some common sense. If you need to provide a very generic abstraction that's flexible, take the time to do it properly. Otherwise, if you need something that makes your code more readable, better, and have less repetition, then this can be the best choice. And also, language and library alternatives might come. So coroutines might supersede higher order function for asynchronicity, and ranges might be better for dealing with sequences. John? Yeah?
Time to take a silly question.
Sure.
Okay, so I looked up the definition of a higher order function, and I have a question for you. So is a function that takes no arguments and evaluates to a non-higher order function, a higher order function, and why?
So you said a function that takes no argument and returns what?
A non-higher order function.
A non-higher order function.
Is it itself a higher order function?
Is it a higher order function? Okay.
Based on your definition.
Based on my definition, it would be a higher order function because one of the bullet points is it either takes a function as an argument or returns a function as a return value. So I would say yes.
So I have 6 characters to read to you. Open paren f, close paren equal g, where f is the original function, g is the function returned, and g is not a higher order function. Therefore, since f is the same as g because it's a constant, I guess it's not.
Yes, I get what you're trying to say.
You just need to expand the definition a little bit. So
Yes.
It covers that case that I was telling Daniel earlier when he said he was half right.
So that's interesting. So if you have two functions, so if you have a function that returns itself, basically,
You have a function that returns something that is not a higher order function.
a function returns something that is not higher order function.
And it
Okay.
doesn't take any arguments, so it's a constant.
Okay.
Then open paren f, close paren, and it returns g equal g because it's the same thing.
I'm not sure if it's the same thing, but
How is it different? Because the function always returns g, and that's all you can do with it. So once you have f, you have g, and in math, there isn't anything else.
from a mathematical point of view, I agree with what you're saying. I'm thinking about it in terms of C++
Might have a different
entities.
address.
Okay.
It's a different G, right?
So in computer science, your definition is fine. In math, it might be problematic.
I have to think about that. It's an interesting thing. So yeah, the comment is, if I try to paraphrase it, on a purely mathematical level, if you have a function that returns a non-high order function, it's
And it's constant.
and
takes
it's
nothing.
and it's constant, so it takes no arguments.
It is in fact the thing that it returns, period.
It is ambiguous, at least for me right now, whether that is a higher order function or not. So I might have to
Sure.
think about it.
Okay.
So, yeah, so I mean that's just a function that's returning a new instance of a function. So I mean it's just uncallable. So if G itself is some consumer, like it's something which you then can feed things to. Like you have two now distinguishable instances of G, right? Like
Yes.
if you have something which is a counter, like that's a canonical example for like you had your thing earlier where you're like returning a new you had a thunk, returned an instance of like the horse or whatever it was.
Yeah, yeah.
So if you had something which was a counter, so you say, hey, produce me a counter. It hands you back a counter. You use counter one to count something in one case. Call it again, counter two, count something in the other case. I mean, the objects, the thing is not itself. I see. Yeah,
We'll
it
talk
is-
about it later.
sure.
I'm
Yeah,
sorry.
yeah.
I wanted to
Yeah,
be a
yeah.
quick one.
That's
In
fine.
math, they're the same. In computer science, they have different addresses,
Sure.
which is why computer science isn't math.
Yeah, that's fair. That's fair. I would say fortunately. Yeah, other points is that they don't play nicely with control flow on the color side. You can't really return, break, and continue on a lambda body, even though you know the lambda body is never going to escape where it's being created. You can work around this. For example, you can return some sort of type that you can check with on your abstraction whether it is a return, continue, or break, and then simulate those things from the abstraction, but that would complicate the implementation of that, which defeats the purpose of using a higher order function in the first place. So that's a drawback. In 17 and 20, lambdas are more powerful. In 17, we got conceptual lambdas, and in 20, we have template lambdas, which are, lambdas with a template syntax, but in 14 we also had generic ones. And there are some proposals that might have helped make this a little bit nicer, like P0573, which is terse lambda syntax, but that didn't fly so well with the committee, so we have all the boilerplate for the higher order functions. Okay, so that was the first half of the talk. Second half is about function ref, and this is where I would like some input on what's going on. So, what options do we have to implement high order function? So far I've shown like template arguments, but we can do multiple things. So the most basic one is pointer to a function. So imagine writing some sort of maybe calculator where you want to pass your operation as a parameter. So this could be, for example, an addition, subtraction, multiplication. And one way you could define that is by having this operation function. It takes a function pointer f that takes two integers and returns another int. And then inside of the body, you do your f with some values. So in this case, this is a higher order function. We're using a normal function pointer, not a template parameter. And this is fine. It works with non-member functions and stateless closures, so that's good. But as soon as you have any stateful callable object, like a lambda that captures something, or some struct with some state in it, then this doesn't work anymore. You cannot bind it to the f function pointer. However, it has very small runtime overhead. So if you have a single TU where the thing you're passing to operation is available, then everything is going to be inlined quite easily by the compiler. It's also constrained with an obvious signature, and by that what I mean is if you have a template parameter, it would be just an f or a t, and you would have some sort of enable if to constrain it. But here it's really obvious that returns an int and takes two integers. So as part of the signature, it's very easy to see what f is supposed to be. So that's one option. It's not great because of the second point, but it has some benefits.
I have a good question.
Sure.
For consistency in the very slide, would you put the star before the f in the return line?
For consistency, would I put what star? Sorry.
Star.
That's in C, C++. Would you put star?
Oh, okay.
I know, but for consistency, that's my question.
Okay, the question is, would I put a star for consistency or not? Just a detail, I haven't thought about it. If I can be consistent, I'd rather be consistent, but...
The reason I ask is because you're going to have a function reference. So it makes the difference whether it's a function pointer or a function reference.
Yes, so in this case, I would say that function ref is you need to see it as a reference to any callable. A function pointer orthogonally is a technique you can use to implement high order functions. So I'm going with that mental model for now. We've seen template parameters, and this works really well. Is zero cost abstraction in a certain way because the compiler has all the information it needs. It works with any function object or callable if using std invoke, including one that has state. And however, it is harder to constrain because you would have to put some sort of enable if or some sort of decal type with expressions fine. And the main problem with this is that a template parameter has to be defined in the header. Every time you pass some sort of closure or function object is going to be in a new instantiation. So this might degrade compilation time in large code bases and also create coupling between interfaces and definitions. One point I also want to make that in 20 we finally have concepts, so the third bullet point might be a little less true. It might be now easy to constrain them by simply saying invocable of int that takes two integers, so it would be quite nice. However, what I care about is the fourth point, which is the coupling between the body and the interface, and that might degrade compilation time. Yep.
Will modules do anything to that, or?
So the question is, would module do anything to help with the compilation time? So as far as I know, modules, when you export a template, you're going to basically export the AST of this entity, and then the consumer of the module will still have to instantiate this AST thing over the type. Please correct me if I'm wrong, I'm not an expert on modules. So you would still have to do that instantiation step, which might be expensive with your compilation time. So I think it might help, but you still have that problem.
So it's only the AST, not the bindings to the first stage of name lookup.
So it's only the AST, not the bindings to the first stage of name lookup. I'm quite sure it does export a more abstract thing, not the first stage, but I'm not completely sure about that. If anyone in the audience knows. Okay. SCD function is another option, and this is what C++ beginners like to use all over the place and then wonder why their code is slow. And it works with any function object or callable. However, since this is supposed to be a generic polymorphic wrapper over any callable with a given signature, it's really hard for the compiler to inline or optimize. And this can lead to significant runtime overhead. And now this is not something set in stone, because maybe in the futures, compilers might be able to optimize this more aggressively, but right now there is a significant cost that you can measure about a CD function. Yes?
It also has, what you found the function has to be copyable, right?
Yes, another drawback is that a CD function, as Ben mentioned, is not perfect in its design. For example, the callable that you give it has to be copyable. It doesn't support move-only callables. It has a bunch of other annoyances, like you cannot force the callable to be constant or accept and stuff like that. However, this is really easy to use. It is constrained with an obvious signature. It supports anything, and it's trivial to use and create interfaces with this. Another point that's a little bit of a stretch, but I like to include this, is this has unclear semantics. It can be both owning or non-owning. Like if you instantiate this with a reference wrapper, then it behaves as if it's a reference to a callable. However, in all other cases, it behaves as if it's owning the callable. So this is kind of a stretch. It's not a big deal, but it would be nice if we could make it clear in the interface where we want a reference or ownership. So this brings us to FunctionRef. This is the paper I proposed for C++ 20, and there's a high chance of making to 20, worst case scenario 23. And as you can see, there's a syntax very similar to function. You just have your function ref, and you provide your return type and argument types, and then you can invoke it as normal. So this works with any function object or callable, like SCD function. It has very small runtime overhead. This is comparable to function pointers. So if everything is in the same translation unit, it's going to be in line and it's going to be very fast. It is constrained with an obvious signature. It has clear non-owning semantics. So when you see function ref, it's going to be a reference. It doesn't own anything. And it's quite lightweight. So think about it as string view for callables. So in a nutshell, function ref of a signature is a non-owning reference to any callable that supports the signature. The parallel I mentioned is SCD string is the owning type and string view is the view only type. SCD function is the owning type and function ref is the view type. It doesn't own or extend the lifetime of the reference callable, which means this is going to be efficient, but it's also going to be dangerous because it's easy to create dangling references. It is lightweight, friendly to no-except and compiler optimizations, and it's also trivially copyable. I proposed this in P0792 and it's currently in LWG. There were some notes in Kona, and we're going to go through some of the problems to see what you think, but it's possible they will be in 20. And many thanks to the people over here that helped a lot with the proposal. Yep?
Question, so to have a function ref, somewhere I have to have a stud function variable that it refers to?
So the question is, to have a function ref, somewhere do I have to have a stud function? That's one option, but it doesn't have to be a stud function. It could be a lambda, a closure type with anonymous type. So anything that you can invoke with a given signature, function ref can refer to it.
But it needs to be a variable somewhere, or I don't know, stuck into a map, or a vector or something. But it has to be it can't be a temporary.
It can be a temporary, depending on how you use it. So if function ref is a function parameter and invoke that function with a temporary, then the temporary is going to live long enough for function ref to do its job. Okay. So it's the exact same scope and problems as string view, like if you're temporary string, all these things. But there's, you can do that. So in practice, why would you ever use function ref instead of a SCD function? There are two main points. The first one is the important one, which is performance. Function ref is way faster. We're going to see some benchmarks. And the second point is, again, clear reference semantics. This makes it like super explicit that what we want is a reference to an existing callable. And sometimes this also matters for semantics. Like maybe you want to take some stateful closure, do some operations with it, and then the mutation needs to be seen from the caller side. So in that case, you want the reference semantics. Second question is, why would you ever use function ref instead of template parameters? So this is very important. It's easier to write, read, and teach. So people can get started with function ref more easily than understanding what enable if does or concept and stuff like that. And there is a nice parallel with string and string view and function ref, so it's easier to teach it away. And very important, it's usable in polymorphic hierarchies. So if you have some sort of hierarchy with virtual functions, you cannot have a template parameter as part of your virtual function, but you can have a function ref. And it has better compilation times and allows you to decouple implementation from definition from declaration way more often, which can be important in large-scale code bases. This is the synopsis of function ref, and basically what all it is 2 pointers, a pointer to some callable object, and then a function pointer called erase function, which basically performs a type erasure and allows you to have this ability of calling any callable independently of its original type as long as it matches your signature. You can construct it from another function ref. You can construct it from any callable, given some constraints we're going to see later. You can rebind it either from a function ref or another callable, swap it, and invoke it, and so on. Yes?
So this object is needed if this is a member function?
Yes, and also if it's something like, so the question is the object needed if this is a member function? The answer is yes, and also if it's like a stateful lambda, you need to point to the actual closure object
Yes.
and then to the thing you invoke it. So before I go into the implementation, I want to show you some use cases examples. I did implement this at Bloomberg in my previous team, and we used this in the broker project I mentioned for the trading systems. And one thing we had was this replay map kind of thing. So this is not the actual code, it's obviously been adapted for the slides. And the idea was that for each user of a particular system, we wanted to keep track of all the commands that have been done. And then for debugging purposes, we could replay them in backwards order to see what was going on. So we had 2 maps. The first one was from command ID to a ref counted command object. So these command objects might have a lot of state. For example, it could be buy these 10,000 orders and all the orders that will be there. So if this command is done 2 times or 3 times, we don't want to copy it. We want to ref count it to avoid memory usage that's necessary. And then another map from QID to command ID. You can imagine the QID might be just the user. So a user has a certain queue of commands, and then we have a deck of all the command IDs. And then we can find the actual commands by going to the other map. So now our problem was we have this internal representation, which is quite complicated. We have 2 maps talking to each other through a command ID. How do we expose an interface that allows us to iterate over all the commands of a user without exposing these details to the user of replay map? And we had a few ideas. One of them would be creating an iterator type, but then it would be complicated to write the implementation of the iterator, to jump through the maps and support, lazily going forward. And then we settled on something like function ref. In this case, we have a simple iterate function. It takes a QID and a function ref f that takes a command by const reference. And what this contract says is basically, okay, I give you a QID and an action, and the replay map will invoke that function ref with all the commands of that user. So in this case, the implementation is quite simple. We find the queue with ID, if there is one. Then we go through the deck, and for each element in the deck in reverse order, we find the item in the ref counted map. We dereference it and provide it to the function by completely removing all implementation details about this being ref counted or having 2 maps. So the benefit of this is that, first of all, we don't have to have this in the header. We can split definition and declaration thanks to function ref. It's going to be fast because we don't have overhead of a CD function. And we completely hide every detail about this internal representation from the user. So in the future, if we want to change the way this is done, maybe not have 2 maps, but some sort of even faster specialized data structure, then the user code will not be affected at all. Other example in the same project, this is about polymorphism. We had this thing called the packet cache, and instead of command 0 was just packets that were coming from the network, so this is a little bit lower level. And what we had was a way to replay these packets or consume them. And as you can see, replaying them implies that they're not going to be destroyed. So we have a function ref that takes a const packet ref. But if we want to consume them for performance reasons, we take an R by reference so that the user of the consume function can move from the packet into some location. And we wanted to experiment with multiple caching strategies at runtime. So we had these virtual functions replay and consume, and they basically accepted the function ref. And this is an example of how polymorphism can be useful in this case. And one of the toy implementations, like the easiest one, was a contiguous packet cache, which implements that interface. And in case of replaying, it just goes through the packets and calls the function ref with the packet. In case of consume, it does the same thing, but in this case, since accepting our value reference, we just move the packet into it, and we give the user the opportunity to move again from the packet. And also we clear at the end because we are consuming all the packets. So the idea here is that function ref can give you a lightweight type to implement your polymorphic hierarchies. And there are some cases where you can afford, the indirection of the virtual call. Maybe it's going to be devirtualized, but SED function will be too expensive if you're calling it over and over in a loop, like in this particular scenario. Another one over here, I think is the last example. I think we're doing good on time. In this case, we had this class called node monitor. You can imagine nodes are just machines in the network. And what we want to do is basically do a sweep over all the machines, find the ones that exceeded a certain timestamp for their heartbeat, so ones that were going to be timed out, and then perform a state change on them. So for example, from up to down, or from down to up, if it was the reverse situation. So what we did is have this type def here for a function ref that takes a node ID and a state transition, which was our callback. We used it as part of the sweeping algorithm. And then what we do, we go through the set of nodes, we check if the node is not down, and if the last heartbeat has been, basically, it goes over the threshold. And if it does, we call the callback with the node ID and with the action of changing the state from up to down. Then we erase that particular item from the set because now it's as timed out, and we continue if that didn't happen. So if you see this thing, we have seen this algorithm before. Do you remember what it is? So a couple of slides ago, we saw that this is a consumeIf. So this was one of the cases where we said, oh, we already have this thing. It's called consumeIf. And we re-implemented it like this. So now we simply have a consumeIf on the data, which is a bunch of nodes. Our predicate is checking whether a node is timed out and is down. And then our action is to simply invoke our callback with the node ID and change the state from up to down. So again, this is an example of how, let's say, prematurely creating abstraction paid off in the end because we found this other use case. Okay, so you've seen a few use cases, and I want to show you how to implement function ref. It's conceptually simple, but the devil is in the details, so we're going to see how that is complicated later. The first thing you do is you create a base template class that takes a signature, and then you basically match the return type and arguments by doing specialization. So you can have return and args as part of your body, and you can play around with them. Then what you do is you store a pointer to the callable object, which is going to be a void star because we want to completely erase the type of the original closure. And then you store this erase function pointer that returns whatever the original thing returns, and then it takes the void star and the args of the original function. So the important thing is this void star over here, which is going to be exactly the same as what we are storing in the function ref. So the idea is that erase function will know the original type of the object. We pass our underscore pointer to the first argument. The erase function will cast the void pointer to the original type, and then it will invoke it with the arguments that we desire. So how does it work? On construction, we set a few pointers. So we're going to have our constructor from a template f. So this can accept any closure that accepts our signature, and that's going to be in the constraints part that we're going to see later. And then we basically do our interpret cast from our function f, so we can put its address into underscore pointer over here. So now we're storing the address of the original function, but erasing its type completely. Then what we do is simply set our erase function pointer over here to this stateless lambda that takes a void star pointer, which is going to be exactly the thing that we're storing into function ref, and then our arguments, and returns the same thing that the user has described in the signature. And the body of this thing is going to be basically what I mentioned before. It takes our void star pointer, casts it back to the original type, which is available here because we have f in this context. It dereferences the pointer and then invokes it with the arguments that were provided to the erase function. So what we're doing here is the erasure is done here on this part, where we set the underscore pointer, and getting back to the original type is done inside the erase function, as we do have the f information as part of this scope. Does that make sense?
Would you put ampersand after arguments?
Here? The question is, would you put double ampersand of the arguments? I think you can do that safely. It would be I think it should be fine, yeah.
You're doing perfect forwarding, so you have to.
Well, you, regardless of whether or not you put double ampersand here, you need forward here, because in the signature, you,
Reduce context.
well, in the signature, some of your arguments might already have value categories, right? So if you don't put the forward, it's still going to be incorrect. So putting the double ampersand here would be an optimization, but it wouldn't make it more correct than it is.
Is it come from the outside?
Yes, arcs come from the outside, yeah, and they can have refs, so that's why you need the forward anyway. But a double ampersand would be a reasonable optimization. You had something, or? Yeah.
I should point out this is not a typical use of forward, but it is correct.
Yes, I agree with that. It's not typical use of forward, but it is required here because even though arcs are not deduced, they can have a ref or double ref, so we want to retain that. Yeah.
Is there a reason why you're not using invoke?
Is there a reason why I'm not using invoke? I think this is just slideware. It should have.
Okay.
This might work in 4D.
Sorry?
Invoke, you only have the C plus and 17.
Yes, but so invoke is not in 17, but I should use invoke. There's no reason why I'm not using invoke. It's just simplicity here.
Does the function do everything that invoke does? I mean, I know it's pre.
Yes, a cd function does everything that invoke does.
Point at the mem data.
Yes, and function ref is defined to work with any callable, so a real implementation would use invoke. So this is just for simplicity in the slide.
That's because it would be more general.
It would be more general. You could say something like, you can have a function ref, I think I'm going to show that later, but you could have a function ref that takes struct as the first argument, and then you instantiate it with a pointer to member function, and then you can call that with struct instance and it will work. So it's the same as an std function in that case. Okay, so the last missing piece is what do we do when we invoke this thing? We simply go through erase function, which is our type D eraser. We pass our pointer as the void star argument of the lambda, and then we forward all the arguments again to the original one. So yes, this could be double ampersand again, and the forward is required regardless for correctness. This.
So the function call operator is faster in this case than it would be for std function?
So is the call operator faster than it would be for a std function? I think that the call operator would have the same performance here, unless it depends on the implementation. Like std function has a small buffer optimization, right? So at least when you are creating the std function object, you're going to have to make that choice, that branch, whether or not you want to go into SBO or not. Then an optimization might be that instead of having the branch on the call operator, then you simply have a pointer which either points to your out-of-place storage or your small storage, and you don't have to do a branch there. So theoretically, it could be the same speed. But the problem with std function is that it's fairly heavyweight in terms of the assembly generates. So I'm not confident in saying that the compiler will have the same ability to optimize this, considering what's surrounding it. But I'm not super confident that. I mostly did runtime benchmarks, so we can benchmark that later. I don't have a benchmark that simply constructs it and calls it multiple times. So this is a full implementation that's very basic. It's missing a lot of features, but that's all you need in practice for a bare bones function ref. Arrays in the constructor, de-arrays in the lambda, and then the operator, the call operator just simply invokes the arrays function with the pointer. Okay, bunch of more interesting things. So this is from the last revision of the paper, and it's basically the wording for the constructor. And what we say here is that, first of all, the constraint is the constructor shall not participate in overall resolution unless this thing is function ref, so we don't want to hijack the copy constructor. And then we say if that's not the case, and if the signature is marked no accept, so if the user specified no accept in the signature, then we only accept callables that are themselves no throw invocable. So this is one way you can enforce your function ref to only accept no accept callables. Likewise, you have CV qualifiers over here, which are the CV qualifiers that were in the signature. So you can also enforce your function ref to take things that are only const qualified. So an example of this is that if you have some sort of struct blob, and blob has a non-const write and a const read, then what you can create is a function ref that has void blob const in the signature. So this is a function ref that takes a blob, returns nothing, but must be const qualified. And then the compiler will prevent you from creating this function ref with a pointer to member function to write, but will be completely fine with you using a pointer to member function to read, as that's const qualified. So this is one way you can enforce the constantness of the thing. Arthur?
Did you test this code? Because I don't think that's what the constant's doing here.
I did. Okay, the comment is, did you test this code? Because I don't think what the constant is doing here. I did test with my own implementation, but there is no guarantee that my own implementation is consistent with my own wording. So that...
It's usually a member function pointer, so it shouldn't even be convertible with function ref that takes a blob. It should be convertible with function ref that takes a blob ref or a blob star. It's a blob by value. And besides that, you don't have to modify the member function pointer in order to call it in either case.
I think I understand what you're saying. So to paraphrase, since this is a pointer member function, then it should not compile if you're taking the blob by value, but just if you take it by reference or pointer. And the const should not mutate, should not imply that that it only accepts constantness of the member function you're passing. But I think that was the original intention, and we can review the wording later and see whether or not my implementation or the wording is wrong, and I'm happy to do that. Yes?
The definite bug is the S instead of blob when you call it.
Yes, that's true. S should be blob. That's a typo. I made this slide yesterday.
Blob, because we want write and read of blob and not.
Yes, that's fair. David?
Why did you attach the const to the function signature as opposed to that blob argument?
That's the question is, why did you attach the const to the signature as opposed to the blob argument? You could do that, but the wording allows you also to provide CV qualifiers on the function type itself. And this is being done to allow you to enforce constantness or no acceptness of what you're passing in. So it might be the case that this is only useful for no accept and not const, but I'm not completely sure about that. I'm happy to review the wording with you later. So please, everyone takes this also as an opportunity to help me improve the paper. Ben?
Are you also providing a default constructor and a conversion to bool, like the function does, or is that?
The question is, are you providing a default constructor and conversion to bool? I think I do, but let's make sure after looking at the paper. Alfredo?
Yes, does this template parameter even matches the specialization you made at the very beginning, where you have R and then parentheses R?
So does the template parameter match the specialization at the beginning? That was simplified for the slides.
Okay. So this is another one with const.
So I think that I'm going to check my other implementation. I cannot say it out of my mind right now, but I have everything here and we have time to do that later. Okay, so but this is the intention. We're going to see a little bit later if that is consistent. And the other thing is the no accept, which is probably more interesting than the const because you can do that with the parameter as well. If you put the no accept after the signature type over here, then you say, okay, I only accept no accept callables. So if you have a function that might throw and one that's well behaved and marked no accept, the first one will create a compile time error when you try to create a function ref with it. The second one will be accepted as the no accept matches what the function ref wants. And this is the same behavior that's described in this paper over here by, I think it's David Cross. And this was being proposed for a CD function, but I think it didn't go through for backwards compatibility reasons. And this was the intention. Let's allow people to constrain even more what these things could do. Conceptually, we could also do that with value categories. So we could constrain the closure to be callable only once or things like that with a double ampersand. That's a value extension, but it's not proposed in the current function of paper right now. Now we get into my favorite or least favorite part, which is lifetime issues. So can anybody tell me what happens here? Yes? Yeah?
It's going to work because it doesn't have the capture, so it has static lifetime.
So you said this kind of work, why?
Because it doesn't have the captures. So that's going to outlive.
Okay, the define cannot work.
It works because that lambda outlives the function ref because it doesn't
So you think is well-defined behavior.
But you aren't passing the function pointer, you're still passing the address of that temporary.
Yeah, but it's not a temporary. So yeah, no, it is a temporary.
No, you still have the
It
void
will work,
star.
but it is undefined
The void
behavior.
star is gonna.
Yeah.
So how many, Peter, you want to say something?
I would say it's a captureless lambda, and that decays to a function pointer. So I believe this code is valid.
How many people think it's valid? Oh boy, I'm so sorry. So Arthur is right. This is undefined behavior. This is not valid code. And we're going to get into the details in a little bit. But what I'm creating here is just a closure object, which happens to be convertible to a function pointer, but it's not right now. And we're just taking the address of this closure object of anonymous type, storing in the function ref. Then this temporary dies on the other line. So when I call get number, I get undefined behavior. Makes sense?
But you could fix that.
I mean,
Yes, we're gonna get there. Yes.
I was gonna say, I mean, yeah, I would imagine even if this does work, I don't think it should, right? Like this is strange. Don't do that.
I agree, no, completely. The comment is this is strange, don't do that. That's true. But you know, after StreamView was released, how many people were like, this thing is useless, it doesn't work. But people will undoubtedly try to do this. It's about teaching that this is not the use case for function ref. But it's important to talk about this and see where the problem lies. So now I'm going to disappoint you even more. What happens here, in your opinion?
What I explained.
So you think it's well behaved?
I guess so.
I'm sorry, it's not well behaved. This is as well undefined behavior. And
Why are you doing strange things?
I'm doing strange things. Yes, I'll explain. Oops. So what we have here is get number. We're taking the address of get number, and then we storing in the function ref. But we defined our constructor as always taking the address of whatever we're passing in. So in this case, we're taking the address of the address. Why does this work? Like, why doesn't this cause a compilation failure? Well, let me explain. So in general, function ref has the same lifetime problems as string view. So when you use it as a function parameter, which is the most recommended use case, is the most useful one, everything is usually fine, because what you do is you create the closure, you call the function. So in the call frame of in the stack frame of the function, the closure is always going to be active, even though it's a temporary. So that's fine. In other cases, there might be valid uses for function ref that's not function parameter, but you have to be careful in order to avoid dangling references, because this doesn't own anything, it doesn't extend anything. But why do non-member functions present lifetime issues? Like, why does the previous slide compile and give undefined behavior? Well, it's consequence of the wording and what pointers of member to functions are. So the wording says that anything that satisfies is invocable with return type, arguments, and function is valid. And then in this case, what we're basically checking is this pointer to the function invocable, and that's true. So in C++, a pointer to a function is considered an invocable. So both the static assertions on the bottom pass. Yes?
Can't we just give another constructor that works with the function pointer?
So yes, the question is, can we just give another constructor to function pointers? I'll get to that.
So is it the same as forbidding a constructor that takes a function pointer?
We could differentiate on this situation, but we currently don't. And I want your input on this, because it's not straightforward to say, yeah, we should do this. There's also a drawback.
Are we victim of C here?
No.
Sorry?
No, but the fact that you can just arbitrarily apply as many styles as you like.
That's why I asked the first question.
Yeah, that's fair. Yeah. Okay. So if we go a little bit deeper, you see that the constructor always takes the address of the callable. So in this case, we're storing a pointer to the function pointer, which, works in the normal use cases, because if this is a function parameter and you pass free function as to construct a function ref, it just works. However, we could make this case work even if it's not a function parameter. We could detect this and fix it, but I'm not too sure that's the right thing to do, because first of all, we would have inconsistency with pointers to member functions, as they do not fit in a single pointer. So now if you have something like function ref equals ampersand foo, it would work. But if you say equals s : ampersand foo, it will not work anymore. It would be dangling. And The other point is this is not how you're supposed to use function ref, so it's kind of unusual. Is it worth making the wording more complicated? I don't know. I'm happy to hear your thoughts. Peter?
So if you don't want to support that case, I would still provide the overload and delete it.
I cannot do that. So the comment is, if you don't want to support that case, you can delete the overload. But then you would prevent that case from working where the function ref is a function parameter which is well behaved. Arthur?
I was thinking about this before you got to this slide, and as you were saying, it decided, no, you really, really, really don't want the special case function pointers, because function ref is supposed to have reference semantics. If I have a global variable function pointer type, and I get a function ref to it,
Yeah.
and then I change my global variable, I don't want my function ref to have captured a copy of it earlier. It needs to have reference semantics.
Yes, that's a really good point. Let me paraphrase. So if we fix this, depending on how we fix this, it might be the case that if we have a global function pointer, we take a function ref, which is supposed to have reference semantics to the function pointer, we would like that to be reflected if we change the function pointer. So having the special case might break that semantic assumption.
Reference wrapper style way of doing it.
The comment is, this kind of reference wrapper style doing it? I would say yes. Okay, so we solved this one. Maybe. Maybe. Second thing that I'm really sad about is constexpr. So the current revision, I basically put constexpr where I thought it was appropriate. And even though, for example, just the copy constructor could be constexpr, the main one couldn't be because it uses reinterpretcast, which is not available at compile time. So my idea was, let's just put constexpr where it could work in the future, but the standard says that if there is no possible way you could create this object at compile time with constexpr, then any use of constexpr is ill-formed. So I think I will have to remove all the constexpr from the interface, and this is quite sad. First of all, because the inability of making this constexpr will create some sort of fracture between the runtime and compile time world. Now, if you have your thing that takes function ref, you cannot use a compile time, so you need either to use a template parameter or implement it to be constexpr. It's quite annoying. And I don't know what can we do about this. So if we ever get a constexpr friendly cast from void star to T star, then this problem goes away. But as far as I understand, that would require a lot of implementation effort because they would have to have their own memory model in the interpreter. One other thing we could do, we have precedent for bitcast, initializer lists, and stuff like that. We could just have compiler magic for function ref, and we say, is magically constexpr. I think that I would be kicked out of LWG for proposing that, but it's worth a try. So if you have any thoughts on this, let me know. I think this is a more complicated problem because it will require relaxing constexpr by quite a lot.
I think it's more likely you would be kicked out of core.
Of course, yeah. Arthur?
I feel like you might get this for free in Funky actually, but is the only problem the constexpr on the operator prime brand?
No. So the problem is in the constructor, because when you take f, right, which is going to be your closure type, and you have to reinterpret cast that to void star. And
Static cast that to void star, that's not a problem for constexpr.
but then you have to cast it back from void star to T star.
Only in the operator prime brand. Is that right?
Yes, okay.
So that's the only one constexpr that's a problem. Everything else, it could be a literal type. You just couldn't call it in a constexpr function. That's not too bad. Static cast to void star is okay, but out of void star.
Yeah, okay, that's a good point. So the comment is that the going from T star to void star is okay in constexpr, but the other way around isn't. So the only problem would be in the call operator, all the rest could be constexpr. That's a good point, okay. I'm still sad that it would be useless basically, but but at least we can have constexpr there.
Can you do static cast on references? Static cast key ref?
I think you can, but it doesn't help. It doesn't help. The problem is that we're storing the thing as a void star.
Oh, right. So
Yeah.
Additionally, oh yeah, right. You're gonna start a void.
Yeah. Peter?
Could you provide specializations for your function ref thing? To make, let's say those that could work.
Okay, I see what you're saying.
Those that couldn't.
So the proposal is providing specializations for function ref with given things.
Yeah.
I don't think that would work because you can only specialize on the signature, right? And then if you have two different types that bind to the same signature, you still have the same problem. How do you erase those things? So good try. Yeah.
I would say just on that topic, I think it might make it a little harder for one of your initiatives here is to make this more teachable. And now you have, in this subset of cases it's const expert, in this subset it's not. But I swear this is super teachable.
Yeah.
I understand that's const expert, meta magic, whatever. Maybe you're not using it for novices or whatever you want to call people that you're teaching.
Yeah, it's a good point. The more complexity, the more special case we get into this, the harder it becomes to teach, and it kind of defeats the purpose. Okay. One more thing. This was an idea suggested by Adam N. Can't remember its surname, I'm sorry, but it's known as Yak Online. And the idea is that sometimes it's really useful to have multiple signatures at the same time. So what it wants is something like a function ref where you can basically provide, two signatures at the same time, like it takes int and returns void, or takes nothing and returns double. And then you can invoke this, you can construct this function ref by providing an overload of those two things. So any callable that supports both the signatures can be used as part of this function ref. The motivation for this, instead of basically having a variant of function refs, is that this is more efficient to implement because you only need a single void star pointer, and then you need all the erasure for the other signature. But you don't have to repeat the void star pointer over and over, which can be beneficial. So I don't have personally any use case. He had compelling use cases for this. In general, I inclined to say this might be a backwards compatible future addition, so we don't have to do it now. But in the future, if we relax the thing, it might be fine. But then there's always that thing called ABI, which is a problem. And we could also provide something like a multi-function ref. But then we have two types. We also want multi-SCD function. And in the end, maybe it's not justifiable. If you need this kind of thing, which is a very special use case, write your own. I don't know. So other things to think about. Okay, so let's get to the last part, benchmarks. I think I have enough time. So what I did is basically use QuickBench, which is an online tool, which is really cool. You simply write your code on the left-hand side with Google benchmark syntax. You run it, and it provides an interactive graph on the right-hand side showing the runtime and the assembly. And I also use Simon Brand's function of implementation that shows you how much trust I have in my own implementation. And it's freely available on GitHub. I think it follows the revision quite well. The scenario was simple, just invoke a higher order function in a loop over and over again. And it was just trying to measure how much overhead the abstraction that we're using has. So the actual body of the thing is very trivial. So I tested with a template parameter, function ref, SCD function, with and without inlining. Yep.
Did you compare that if you call the function directly or through a ref in Godbolt or the assembly?
I did some assembly tests in the past, and what I've seen is that basically function pointer, templates, and function ref have the same generated assembly for the same TU with inlining enabled, and SCD function has always more baggage to it. Peter?
Just from the top of my head, the problem is the void casting thing for type erasure. Would it be possible to have things like, a variant of those things where you don't have to cast, and then the generic part does work?
No, because the comment is about the void star before. Would it be possible to have a variant of those objects? You don't know in advance all the objects you could take, because you could generate a new one on the spot, like lambda, which is an anonymous type.
Let's say you could have a special case for function pointer with that signature.
Just for function pointers. Yeah. Yes, but
I just want my function pointer to work.
Yeah, you can make that work, but. So this looks a little bit like this. We have a bunch of benchmarks. The first one is just takes the template parameter and calls it. Second one takes the SCD function and calls it, and so on and so on. So what we're simply benchmarking is the overhead of the abstraction itself. And we use this do not optimize thing, which prevents the compiler from doing crazy optimizations, like removing this if it doesn't have any side effect. We also have the same versions without inlining. So we explicitly disabled inlining to see how that affects the behavior of these things. And then the way we simply call this is by creating a Google benchmark thing that over here loops over a state. And the state is basically some Google benchmark provided thing that knows how many times to iterate. And then we call this function by providing a closure, which will always construct the abstraction, invoke it, and destroy the abstraction, and so on. David?
That no inline attribute that you used in the previous slide,
Yeah.
does that apply to the body of that function?
It applies.
Or the colors of that function?
So no inline in this slide, what does it apply to? It basically prevents the compiler from seeing what's inside the body of this function and then doing optimization around that. So it's forced to have the call to this thing. So for example, this SCD function means that you always have to construct the function or function ref, while before it could simply see through the whole thing and say, I'm not constructing anything, I just call the actual thing. And we do that for every single thing. So the benchmark is really simple. It might not be, again, it's a micro benchmark. It might not be realistic in major use cases, but it does measure the overhead of the thing. So this is GCC 8.x, 03, libstandard C++. You got links as well if you want to try it on your own. And as you can see, template parameter and function ref with inlining, they are exactly the same thing. So if you have inlining enabled and everything is the same to you, function ref is exactly the same as a template parameter. With inlining enabled, a SCD function is 7 times slower than either template parameter or function ref. So obviously in this benchmark, there's also the cost of the construction of a SCD function because we are creating it over and over. But if you have a model where you have a higher order function and you call it over and over again, that's exactly what's going to happen. Like with this model, you're not going to store the function and then call it multiple times.
Did you try that benchmark where the function was created and then you just went through it?
So the comment is, did you try it with a function already created and just went through it? No, because like the thing I'm trying to model here is the higher order function thing, where you have your own thing and pass the action. I would expect the function to do a lot better in that one, and I should try it and report back. So it's not intentional to make this look nice. I was just trying to model the higher order function thing. Yeah.
So in the higher order function case, why are you saying they would have to construct it everything?
Because your signature would take your action, right? How do you take the action? You take a SCD function,
Sure.
and then on the color side, yeah, on the color side, you want to provide a temporal lambda. You don't want to store the thing or not. Without inlining, it's a little bit different. So template parameter is very good, just 3 times 0.5 slower than normal template parameter. And now function ref shows some overhead, but still it is faster than a SCD function even without inlining, and it's roughly twice as slow as a template parameter. So this is GCC, and results are very consistent with Clang as well. I tried Clang 7.x, and again, template and function ref are the same with inlining, and SCD function is 8 times 0.5 slower, and we have the same hierarchy without inlining. So what conclusion can we, I also tried with libc++, same thing, SCD functions are a little bit better. So what conclusion can we draw from this? When you have inlining and everything is sent to you, so all the best case scenario happens, function ref is as fast as a template parameter, and SCD function is at least 7 times slower than function ref with inlining enabled in the situation where you always construct it. When inlining doesn't happen, then function ref is around 2 times slower than template parameters, but still beats SCD function as it is 1.5 times slower than function ref. So function ref is optimizer friendly and tried with inlining, and in general it's always faster than SCD function, and the ratio depends on whether or not you have inlining enabled. Conclusion, any function accepting or returning an order is a higher order function in the computer science world, but that might be different in the math.
I totally agree. I've been thinking that you're absolutely right in the computer science world.
We have many examples of that in C and C++ standards, and varied use cases like avoiding repetition, inverted control flow, asynchronicity, metaprogramming, and they're highly usable thanks to lambda expressions. They're also easier to write compared to the other alternatives that we've seen before, and in general, I would like you to go fully functional when you can, but sometimes you have also co-workers, and in that case, you can, slowly integrate these things where it makes sense. Function ref is just a non-only reference to a callable with a given signature. It's only way to standardization. Hopefully it's going to be in 20. Worst case scenario 23. It's lightweight, trivial for the compiler to optimize when it's inlined, and it has clear semantics and higher performance compared to the function when used as implementation technique for higher order functions. You can start using it today. You can write your own by following the specification in P0792 or use Simons-Bennett implementation, which is quite good. Thank you. Okay, so I think we have time for questions, right? This is the last slot. Yeah.
Okay, so I think you shouldn't make function ref default constructible. But in case you're in doubt still, maybe answering these 2 questions will actually make you decide whether you you make function ref comparable.
Okay.
Whether you
I do have the paper, yeah.
operator ampersand on function ref,
Okay.
and whether you implement the function PTR plus.
Okay. So you want a difference between function ref and function PDR, where PDR is default constructible.
Right. It can be implemented the same. It's just that one is the pointer of the other. And
Yeah,
that's why my question about operator ampersand and equality.
Okay, so according to my own wording, this is not default constructible and doesn't have the ampersand. So I remember we had this discussion in EWG, and we decided to make this a reference and not a pointer-like thing. So it always has to be initialized with something valid.
But PTR reference, right?
Yes, yes.
Yes, you can implement the PTR separately.
But you can still initialize it with something that blows up.
Yes, yes. You can do the same with a reference, so it's fine. Yes?
Did you? I didn't. Yeah. Did you have any? Because one of the things that you contend, I buy is that function ref is more inliner friendly than STD function.
Yes.
Did you have any benchmarks that actually demonstrated that? Because I don't think I saw it. Like you either disabled inlining and it just happened, or you enabled inlining and they were trivial and always got inlining.
So in both cases, you saw that there was a difference in performance. Even with inlining enabled, like STD function is not able to be inlined as. My guess about what is the case is that STD function has machinery inside for the small buffer optimization and stuff like that, and it just throws off the optimizer. It might be the case that in the future it does a better job, or maybe STD function will be implemented in a way that's easier for the optimizer to go through layers. But I have not researched the reason why this is the case so far. So sorry for that. David.
In the case that your parameter is a callback to a function, and that callback is invoked asynchronously.
Yes.
I guess in that case you wouldn't want to have a function ref parameter?
Yes, exactly. So if you are expecting your call to be asynchronous, if you don't know what the lifetime of the callback should be, then you shouldn't use function ref. So function ref is about, I feel like you can make it work with the synchronicity if you're really careful, but it's more about you are in the same stack frame and you know that everything resolves properly in that particular stack frame. So I wouldn't encourage using function ref in asynchronous scenarios. Yeah?
Just follow up on that. So unlike string view, string view you can take that in as a parameter and then store it as a std string data number or something like that by making a copy.
Yes.
But there's no way to make a copy of these function references.
Yes, absolutely. So
that comparison kind of breaks down in that spot.
Yes. So the comment is really valuable. It says that David says that basically string view, you can take it as a function argument and then you can store that thing inside as a string, because what you have is basically a range of contiguous characters, so you can just copy them into an STD string and get ownership of the thing. With function ref, that's impossible because you erased all the information about the function, but we didn't erase the copy constructor or something like that. So you cannot actually store it after you take it. You just have a reference, and that's where the comparison starts to break a little bit. I think it was Arthur.
Yeah, to piggyback on that is interesting for teachability. I mean, this is still a great idea and should still do it, but it is not the same relationship as string to string view, because you can implicitly convert a string view back to a string, and you can implicitly convert a function ref back to a function. But I mean, you can. It's implicitly convertible function.
Yeah, but it's gonna.
But it won't be the right thing, so you have to be careful there.
Yeah.
My question was going to be, are you mandating that function ref is trivially copyable, and if not, why not?
The question is, are you mandating this thing is fairly copyable? I wasn't. I got strong advice to do it, and I'm doing it now. And I get that it's important, so yes.
In principle, you can have a value type associated with this reference, because when you construct the object in the same way you type erase the calling operation, you can type erase how to copy it.
Yes, that's what I was trying to say. You could also type erase the copy constructor and get something that, another erase function which has a target and copies into the target. You can do that, but then you get to the point that this thing is going to become large, and the function ref itself is going to become bigger because you would have two function pointers stored there. So where do you draw the line? Do you want copy, move,
And then you have to decide what's the value type, the STD function itself.
Yeah, exactly. You would have to decide as well. I think honestly a function ref is really useful, but the only fact that it has to exist is a smell for the language, because what we're basically doing is we have a concept and we're creating a type-erased version of that concept. So what I would like is some sort of facility to do that on demand. So I have a concept that's like callable. Okay, I can do virtual concept or something like that. Because doing that for every single concept that's useful, providing a view over that is not scalable. And as you can see, some people might want to erase multiple things. Some people might want to erase only a single thing. So this should be some sort of language facility or something like Louis Dion did with his, I think, Dino library. So something along those lines that gives you more freedom. But as a vocabulary type, this is useful for interoperability reasons. Okay, any more questions? Cool, then I think we're done. Thank you.